Hi, folks, and welcome to our lesson on Newton's third law. Okay, and this third law is just simply stating that for every action, there is an equal and opposite reaction. Okay, or sorry, for every action, I should probably change it. For every action force, there is an equal and opposite reaction force. Okay, now we say equal in magnitude, but they are opposite in direction. Okay, and that's very important. Okay, so for every action force, there is an equal and opposite reaction force. They are equal in magnitude, but they are opposite in direction. And any of these interactions involving these two forces, we will call those action-reaction force pairs. Okay. So let's look at a couple examples to understand how this is working. Okay. So once again, Newton's third law, for every action force, there's an equal in magnitude and opposite in direction reaction force, and we call these action-reaction force pairs. Okay. So the first example that we have is if you hit a baseball with a bat. Okay, so if you hit a baseball with a bat, now this action-reaction force pairs that we have for this situation here is the bat hits the ball, okay, but at the same time, the ball is hitting the bat. Okay, so that's our action-reaction force pair. You're swinging the bat at the ball. Okay, so swinging your bat hits the ball keeps going, right? And it's just that option, that force. So not only are you hitting the ball with the bat, but essentially that bat is also hitting the ball at the same time. All right, let's take another one here. Let's take a look at example 2. And a sprinter running a race. Or a sprinter starts running. All right, well, for this one, the first part that we have is in order for that runner to start running, okay, the runner pushes off the ground. All right, so the runner is pushing the ground, and the reaction force that we see from here is that the ground pushes the runner. Okay, so we got this one sitting here. All right, and one last example that we have here is a fish swims through water. Okay, fish swims through water. All right, and the two ones here is the fish pushes the water out of the way as it swims through it. And at the same time that the fish is pushing the water pushes back on the fish. Okay, so each one of these situations, we realize that we have this interaction, this action-reaction force pair. Okay, the bat is hitting the ball, at the same time the ball is hitting the bat. The runner is pushing off the ground, and the ground is pushing back on the runner. Okay, the fish pushes through the water pushes the fish. And all of these are in the opposite directions. Okay, the magnitudes are the same, but they're all happening in the opposite directions. Okay, hopefully that helps with these first couple examples. All right, let's move on to another example here, and hopefully this helps a little bit understand why, a little bit more about these forces. Okay, so let's imagine a bug hitting the windshield of a semi-trailer. Okay, so a bug hitting a windshield of a semi-trailer. What force pair occurs? Well, in this one, we have the truck hits the bug. All right. Well, and the bug hits the truck. Okay, that is our force pair. All right, the action-reaction. Now, which force is bigger? In this situation, actually, neither force is bigger. Okay, and now I said that when we talked about this in the first place, that this is an action-reaction force pairs, that they are equal in magnitude and opposite in direction. And if we think about this situation, okay, here is a terribly drawn truck. Okay, here's the windshield. All right, our truck's going this way, and we've got our little bug. Okay, flying into the windshield. All right, so this is where we get that opposite situation, right? The bug is going this way, the truck is going this way. Okay, so we have that situation. And now, neither one of these forces is bigger. Okay, now, the reason why we see such a more impact on the bug instead of the truck, this has to deal with the mass. Okay, so we want to go back to remember that force equals mass times acceleration. Our force is the same, but because our mass is different, we have a different acceleration on each of these. Okay, so which object has greater acceleration? Well, in this case, the bug has the greater acceleration. Okay, because acceleration is just going to be force divided by mass. Okay, and since our bug is much less than 1 kilogram, our acceleration is going to be much larger, whereas our truck is probably closer to like 1,000 kilograms, making that acceleration smaller. So because of that difference in the mass, you don't notice the impact on the truck. You don't see the change of acceleration on the truck, but you definitely see the change in acceleration in the bug. Okay, so the bug has greater acceleration. Okay, the bug has greater acceleration because the mass of the bug is much less than the mass of the truck. Okay, and so that's why we see more of an impact on the bug than we do on the truck. Okay, 3 last examples I want to talk about here before we move on to talk about friction. Okay, now 3 common examples that we can think of here would be example 1, recoil. Okay, so if we're shooting a gun, okay, in this situation, okay, the gun pushes the bullet. Now, I know that's not quite exact, but that's essentially what's happening. Okay, the gun is pushing the bullet, and the counter force, or the reaction force from here, is the bullet pushes the gun. Okay, so now anybody that's ever shot a pistol at a range or something like that, you'll notice that you're going here, you shoot, and your hand jumps back like this. Okay, that's because as the gun's pushing the bullet, that bullet is pushing back on the gun, and it causes you to jerk back. Okay, that's that counteraction of the force, right? The reaction force. Okay. Another example we can think of is if a karate master has his bricks laid out on the shelf here, right? And he chops it to crack that brick. All right, well, the first one that's pretty obvious here is the man hits the brick. Okay. And this is the reason that most people get hurt when they do this, is not only is the man hitting the brick, but the brick is in turn hitting the man's hand. Okay, so this is that counteraction force. We are applying that force downwards onto the brick. That brick is also have that same force applied back on us when we hit it. It's that action-reaction force. All right. Hopefully that helps with those two. Now, the third example we have here is a rocket. And so how does a rocket launch itself into space? Well, we ignite gas, okay? And so the rocket pushes exhaust gas, right? So we take a liquid fuel, we burn it, it turns into gas and it expands, and it's that exhaust gas that pushes, the rocket is pushing that gas out. And now because that gas is sitting right below it, the reaction force here is that the gas propels the rocket. Okay, so we have our little rocket here. The gas is the rocket's pushing that gas out. The gas in turn is pushing that rocket up. Okay, it continues to push gas out and it continues to push that rocket up. Okay, so these are those reaction action force pairs. Okay, for every action there is an equal in magnitude and opposite in direction reaction force. All right, next up we're going to talk here about the force of friction. Okay, and friction is created whenever two surfaces move past one another. Okay, so whenever two surfaces move past one another, we get friction. Okay, and we're all used to seeing this. We understand that if we've got, say, a piece of sandpaper on a piece of wood, it's going to not be moving that well, whereas a piece of wood on this smooth surface would move much easier. Okay, so and we've talked about this in the past. Some examples we've done was pushing a sled on snow, where we see almost no friction, and then we hit a piece of gravel and it slows right down because that friction is greater as we're on that different surface. And the reason why this is happening is that on the microscopic level, there are irregularities in the two surfaces, and they catch on each other. Okay, so when you see a smooth surface like this, it's kind of hard to see those irregularities. However, if you looked close enough, you would see that there's little bumps all the way throughout this. Okay, we see that on paper, we see that on any surface. Some surfaces are a little bit more, have more irregularities to catch on other things. And this is essentially all that friction is these two surfaces catching on each other when they rub. Okay, something we've dealt with in the past. Okay, so now that we've described what friction is, we want to understand how we can calculate this in our equations. All right, so our equation for force of friction, right? So we're going to use F, and we're going to use sub F, okay? So this is the force of friction, okay? Now this depends on this Greek letter mu, okay? And the Fn. Okay, where this Fn is our normal force. Right, but let's make sure we understand what these two are. So Fn, we've talked about this before. Okay, this is our normal force. Okay, and this one here is perpendicular to a surface. All right, so normal force. Let's think about this table. This is our surface that we're dealing with, and I put my marker on this. Okay, gravity is trying to pull this marker down, but this table, this surface, is pushing that marker back up. And so in this situation, the way that we have this, f of g equals f of n, right? Because I'm just sitting on this normal horizontal flat surface. My marker is not accelerating, so whatever the force that's pulling it down, force of gravity, that table is pushing back up with the force, the normal force, to counter out those balances. And so we have this situation. And perpendicular, just meaning that if our surface is flat like this, it is pointing straight up. Okay. If I had, say, this angled surface, it would be going, sorry, let's see, so you can see this here. If I had this angled surface, it would be perpendicular to that surface at an angle like this. Okay, so We'll come back to those angled surfaces in the next couple weeks when we talk about inclined planes. For now, we are going to deal with flat horizontal surfaces, and so we are dealing with a straight Fn equals Fg for this week. All right. Now, what's this funny little letter here? Okay, so this is the Greek letter. Pronounced mu. Okay. And now what is it? This is actually the coefficient of friction. Coefficient of friction. Okay. It has no units, right? Because force of friction is going to be in newtons. Our normal force is in newtons. This mu, this coefficient of friction, has no units. No units. Okay? And this mu depends on the surface. Okay? Now, we got a couple different situations going to happen here. Either we are going to be given the mu and have to calculate our force of friction, or we're going to be given the force of friction and our normal force and have to figure out what that mu value is. Okay, we'll get into a couple examples of this in a moment. Okay, but for now, our force of friction equals mu multiplied by the normal force. That normal force is perpendicular to the surface. Okay, it's the force that holds an object from falling down. Okay, and in this case, our mu, it's the Greek letter, or this funny little symbol here is the Greek letter mu. It's the coefficient of friction, and it depends on the surface. So if we're talking about this smooth tabletop, it would have a relatively low coefficient of friction, probably somewhere around 0.1 to 0.2-ish. Okay, whereas something like, say, concrete or sandpaper could be anywhere from a 0.5 to maybe a 0.8 or above. Okay, now the one thing about this coefficient of friction, as far as we're concerned, it will always be less than 1. Okay, coefficient of friction is always going to be less than 1. It is a decimal or a fraction. Okay. Now we're going to come back to deal with some of these calculations here, but there's two things I want to talk about really quickly, and those are two types of friction that we can deal with. We can have static friction, okay, and this is just the friction on a stationary object. Okay, so let's see. Example of that would be based on the coefficient of friction of this little eraser that I have here and this pen and the contact between those two surfaces, my lid doesn't move. However, if I raise it a little bit, the coefficient of friction, the static friction, isn't enough to keep it stationary. Okay, and so then it starts to move. Once we start moving, this is called kinetic friction. Okay, so kinetic friction is the friction on a moving object. Okay, so we get this static is on stationary, okay, and we get kinetic is on moving, right? And we've heard about kinetic, or kinesiology is the study of motion and things like that, right? So kinetic is something that's moving, static is something that is stationary, okay? And so when we're talking about the force of frictions here, so when we are talking about static friction, okay, this is always going to be greater than kinetic friction. Okay? Or we can say that the mu of a static is greater than the mu of kinetic. Okay? So let's think about an example here. We have a box on an uneven floor or a frictional floor. If you start pushing on it, it takes a lot to get things moving. Once it starts moving, it becomes easier to maintain that motion. And that is because of this portion right here. The coefficient of static friction is greater than the coefficient of kinetic friction, which makes our overall static friction greater than our kinetic friction. All right, now that we've gone through all of our definitions, let's take a look at these three examples that we have here. Okay, so example one, a 3.75 kilogram block is pushed along a tabletop with a force of 45 newtons. The coefficient of friction is 0.65. Find the force of friction, find the acceleration. Okay, these are very common type problems, so let's work our way through this. So, let's start off with listing off the information. We have mass is 3.75 kilograms. Is pushed along a tabletop with a force of 45 newtons. So that is going to be our applied force, 45 newtons, and the coefficient of friction, our mu, is 0.65. No units. All right. Next up, we practiced these last week, but we have these free body diagrams that we want to draw. So here is our block. All right. So what do we have here? This block is sitting on a table, a flat horizontal table, and so we have our force of gravity. Gravity's pulling it down. We have our Fn going upwards. All right. We also have this applied force is going in this way, so we have that Fa. Okay. And then opposing that force is the force of friction, or opposing that motion, I should say, is that force of friction. Okay. We've listed our information. We've drawn our free body diagram. Let's take a look and try and figure out the rest of this part. Okay. Question A, find the force of friction. Well, we saw this on that previous page. Force of friction equals mu times Fn. All right. Well, if we look here, we've got our Fn and our Fg. This object is sitting on a table and it's only moving horizontally. So therefore, our Fg equals Fn. So that means I can rewrite this. This is over here. Fg equals Fn. So I can change this to say it's mu times Fg. So our force of friction then becomes mu. Now remember, Fg is just m times g, mass times gravity. If it doesn't say anything, we're dealing with Earth, and so we know gravity is 9.81. So my force of friction, which was originally mu times Fn, well, because we're on a horizontal flat surface, Fg equals Fn, we know that our Fg is mg, so I've taken my force of friction is now mu times mg. All right. Plug in some values here. I have 0.65. I have 3.75. And I have the acceleration of gravity, 9.81. Okay. Now all we got to do is multiply these all out. So 0.65 times 3.75 times 9.81. 23.91 newtons. If we pay attention back up here, our coefficient of friction is what's going to set up our sig figs here, okay? And we end up with a force of friction 24 newtons. All right. Let's move on to question B here. And we want to find the acceleration. All right, well, acceleration, we are talking F net equals ma. All right, well, what's working out here? We got to figure out the F net is based on our winning force subtract our losing force. Well, we've got 45 newtons for our applied, 24, I guess that was 23.91 newtons, so I want to carry those extra sig figs for the time being. Okay, so if F net equals ma, we could say that this is also then F applied minus our force of friction. Our applied force is going to win out over our friction, so our net force is going to be that, that subtraction here. And since we want to find acceleration, acceleration is then going to be our force applied minus our force of friction divided by our overall mass. Plugging in values, 45.0 minus 23.91 divided by 3.75. And I end up with 5.624. Okay. Once again, we want to go back into our sig figs. We are limited by this coefficient of friction to solve these, and so I end up with my acceleration being 5.6 meters per second squared. Okay, and our direction would be the same as the force applied. Okay, so the way that I've drawn this, we would say our direction is to the right. Okay, if there's no direction in the problem, we might not always have to put that direction in there, but we have talked about how all these are vectors. We should include that direction. All right, let's try example number 2. Okay, example number 2. A 0.200 kilogram puck is pushed along a sheet of ice with a force of 0.240 newtons. If it moves at a constant velocity, find the coefficient of friction. Okay, so let's start off by listing out our information. So we have our mass equals 0.200 kilograms. Make that look like a 2 for you. Okay. Still annoying. Okay, and we have pushed along with a force. So this is again our F applied, our force applied of 0.240 newtons. Okay. Now there's another part on here. Constant velocity. Constant velocity tells us we have no acceleration. If we have no acceleration, that means F net is also 0. Okay. Let's draw our free body diagram. We have our puck. We have force of gravity pulling down, our force normal pushing up, force applied, force of friction. Okay, well, we know we're on a flat horizontal surface for Fg equals Fn, that part we know, and now if we have no F net, that means that, well, first off, let's do this. Fn equals Fg, we know that part from this being on a flat horizontal surface. Okay, the puck is not falling into the ice, so that means these two are equal. And then if we have F net equals to 0, that means our force of friction equals our force applied. Okay, so let's take a look here then. If we know, go back to our original formula for force of friction equals mu Fn. We're trying to solve for this mu, right? We want to find the coefficient of friction. That was the problem. So mu equals then force of friction divided by force normal. Well, we don't have a force of friction, but we have our force applied, and we know that since F net equals 0, that these two are equal, so I can change that one. And I also know that my Fn equals Fg. I can plug that one in here. So when we go to solve this then, my mu equals my Fa, oops, we have that value, 0.240 newtons, divided by my force of gravity. Okay, well, this is just mg. We have our mass, 0.200, and we have our acceleration due to gravity of 9.81. Okay. So this is 0.240 divided by 1.962. And I end up with a coefficient of friction of 0.12232. If we go back and we pay attention to sig figs, everything up here is in 3 sig figs. So our mu, our coefficient of friction for this surface of ice, is 0.122. And remember, no units. Okay, so we've gone through 2 problems here. We've figured out the force of friction and the overall acceleration of a block in example 1. We've taken some information and solved the coefficient of friction here in example 2. Let's take a look at the most complex type of problem we're going to deal with in this section, pushing a book against the wall. All right, here we are with example 3. A 1.1 kilogram textbook is held against a vertical wall with a force of 45 newtons. What is the coefficient of friction between the book and the wall? Okay, so I started off listing some information here. We've got this force here. It says held against a vertical wall with a force of 45 newtons. So here's our picture off to the side. We want to label all of our forces that we have acting on this system. Okay, well, we have our force of gravity coming down. We've said that the normal force, actually, let's pause for this is falling if it wasn't held against the wall. Okay, but since it's against the wall, force of gravity is pulling it down. We have our force of friction. The wall is opposing this force. Okay, now this 45 newtons, this is the applied force. We're pushing against with a force applied of 45 newtons. Okay, and our normal force is the force of a surface pushing back against. So if we have this Fa in that direction, that means we have this Fn in this direction. Okay, so let's try and work through this again. We have a book being pushed against a wall. So I'm applying that force to hold it against the wall. The normal force, because it's not being pushed into the wall, that means that the wall is pushing back with that force here. So in this situation, my force applied equals my normal force. So that means 45 newtons of applied force is also my normal force. Okay. We also have force of gravity would be pulling this book down, right? So if I push something in the wall, I've got enough. If I don't put enough force against it, it's going to slip, right? I don't have enough, it's going to fall down. So it's actually the force of friction that's holding it up. My little bit of force of pushing against it is opposing gravity. If I don't have enough, it still slides down. So force of gravity has to equal the force of friction to hold this against the wall. Okay. Hopefully those parts make sense. Very similar to other things we've done, but we gotta draw this free body diagram here to help understand what is happening. Okay, now, let's see, what do we have going on here? We need to solve some situations here. Well, we know that this is our normal force. So what's our formula? We've got force of friction has to equal mu times Fn. And again, we're trying to solve for this coefficient of friction. Well, we have our normal force from here, and we have our force of friction is this Fg. Okay, so once again, we're going to manipulate this to say that this is the force of friction divided by the normal force. Okay. We also know that we have this 45 newtons for our force, our normal force. Our force of friction we said is up here is our Fg. So if Ff equals Fg equals mg, well then my force of friction is going to be this 1.1 kilograms times the 9.81 meters per second squared that we use for gravity. I can now take this equation here, where we're going to take the 1.1 times the 9.81 and divide that by that 45 newtons. And this gives me a coefficient of friction of 0.2398. Paying attention to two sig figs up here, we would say a coefficient of friction of 0.24. And once again, no units on that coefficient of friction. All right. Hopefully that helps us out with Newton's third law and with the force of friction. Okay. Now you have a worksheet attached to these notes here just on force of friction. Be sure to draw your free body diagrams with all force problems. It is a part of any written response question you do, and it's really going to help you to analyze and interpret the situation. Okay, that's why we spent a whole week just working on those free body diagrams. Okay, you'll also notice that I have a another file posted on there which has 4 worksheets on it, kind of encompassing everything we've talked about, all 3 of Newton's laws, and including up into this friction portion. As you're working through those, any questions that you find that are listed as challenge or involve multiple objects, don't worry about those ones so much. Okay, we're going to get into the multiple object stuff next week. Okay, and we're going to start talking about inclined planes. So the only questions I want you to focus on for right now is Newton's 3 laws, horizontal or vertical objects only, no slanted, and only with a single object. Anything with 2 objects, feel free to try it, but I will not test you on that. Okay? Hope that helps. Be safe, stay healthy.